Sairam. Having seen the basic parts of this D block and F block elements, its position and its configuration, let us now slowly dig into the properties of this D block elements. So in the first segment, let us now see about certain physical properties and its atomic and ionic sizes which are there. So in this part now, what are certain metallic properties or the physical properties that we come across in this? It says these D block elements have a high tensile strength, which means that the electronic placement is such that they offer good strength to each other. It also shows ductility, malleability. This is something that you have studied in the school level, where ductility and malleability are the property of metals which can be made into sheets as well as into wires. High thermal conductivity, high electric conductivity, which means that these elements can be used in various electric platforms, can be used as heaters and other segments which are there. This is one advantage of this part which has been present. It also has a metallic luster, which means that it gives a good coloration by itself. We have already seen that these elements can have a property of colored ions, and luster indicates that they are showing a color of themselves. Hard and high melting and boiling points. Now why it is hard? Because these are all metallic forms. These are naturally occurring in the earth's crust, so they are hard in nature. They also have high melting and boiling points. Why this melting and boiling point is pretty high? This let us study with a little bit of analogies from the scientific studies. So melting points, I have a graph here which shows the melting points of various elements of 3D series, 4D series and 5D series. What you see here is that the melting point at the start is increasing slowly, it is increasing, and then suddenly it is decreasing. Later on there is some sort of stability that is seen, and then finally again it is coming down. I am again going to talk with respect to 3D elements here only, where you can see that the starting scandium is missing, ending zinc is missing. Why is this so? This is because the starting series which are there, they do not come in the range of this melting points which are there. Whereas the other elements, why this happens is because, what is the dependency of melting points and boiling points? It is the stability of the compound. In organic chemistry, we have realized that boiling points which are there are directly proportional to something called as van der Waals forces. So what are van der Waals forces that we need to see first? Van der Waals forces are those forces which are present between atoms in a particular compound. So that determines the boiling point. What about melting point? Melting point is dependent on symmetry. The more strongly symmetric a molecule is, the more will be its melting point. So as you see here in this case, titanium which is present having 3D2 4s2. This indicates that the 3D2 which is there, if I take up 5 different orbitals, only the first 2 orbitals are filled, which means that unpaired electrons always like to attract with others. If they are paired by themselves like the way it is in 4s, then they are paired and they are stabilized by themselves. They don't look for other people. But whenever there is an unpaired electron, they cannot stabilize by themselves. They try to look for stability with other people. And therefore, these parts which are there will try to attract more with others. Similarly, vanadium, you come across another electron which is present, so therefore this shows more attractivity. Chromium, as you know, there is an exception in this case where for chromium the 3D system is going to be half filled, 1, 2, 3, 4, 5, and 4s also is going to be half filled. Because of maximum half filled condition, they can be very attractive to others, and therefore this shows a very high melting point, but suddenly you see that for manganese it comes down. What is the configuration for manganese? This is manganese. It is 3D 5 4s2. For this configuration, this is the anomaly which has been present because the decrease is been because of a half-filled stable structure which is present here. Remember that chromium also is half-filled, but then it is half-filled in 3D, whereas in 4s it is singly present and it still goes for attraction. Whereas here, this is fully filled and stable. This is having 5 unpaired electrons, but the good thing is it is showing half-filled stability also. Because of that it goes down, and then if you see for elements like iron and other compounds, you will realize that iron will have one paired system in 3D also, and therefore slowly its melting point, it has raised, but then it is almost similar and then again further coming down and down. For copper it has decreased because it shows the fully filled stability structure in that case also. So this is regarding the melting points which are there, and we see here that in any row the melting points will rise to a maximum of D5. Remember, chromium has D5, manganese also has D5, but that's an anomaly in this case, but because of manganese having 4s2 also. One unpaired electron will be very favorable because unpaired electrons, they like to attract others. Paired electrons, they are fit and fine at their given place, they are very stabilized in nature. So the more the unpaired electrons, melting points will be higher. And similarly, so with the larger presence of unpaired valence electron, the melting points will increase. So as you go above, you will see that for 3D this was melting point, 4D and 5D it increased much more. That is because of the size. Now as the electron filling is more electrons, more protons, with more size, it indicates more interactions which are present, and therefore in comparison to 3D, 4D and 5D will naturally have higher melting points present in them. Similar will be the cases with boiling points, where with an increase in size, the boiling points of the compounds will definitely increase. So this is one important aspect of the physical properties that we see for these type of compounds. So having seen these physical properties, we shall now look at another property which is called as enthalpy of atomization. What is this? Atomization is nothing but forming of atoms. So we know very well that atoms are present. Suppose I take an atom, say like scandium. Does that mean that I have one single atom of scandium with me? Remember that this scandium which is present here will have an equivalent molecular mass present with it. Suppose the weight of scandium is around say 42 gram, it means that in 42 grams I have around 6.022 into 10 raised to 23 molecules, which is equivalent to the Avogadro number which is present. So when so many atoms are present, naturally all those atoms have to be combined together. The energy for that combination is called as enthalpy of atomization. So this energy required for the combination is considered here, and once again we are going to do a study of this part which is present. Let us see the values which are present here in the first place. The value says that for scandium it is 326, slowly it is rising above 473, that's nice. Once again there is a rise of 515, but you see that there is a good amount of decrease at chromium and manganese. Again there is an increase, a minimum stability which is seen, but finally copper is coming at 339 and zinc is, the value is suddenly decreased to 126. That's a massive decrease. Now why do we come across all these factors? At the start there is an increase because an increase in the unpaired electrons of d orbital. Scandium there is one unpaired electron, so more energy is needed to hold the atoms together. Similarly titanium, vanadium, it is more. But when you come to chromium, no doubt there are 5 unpaired electrons in d orbital, but it is showing half-filled stability. Why do atoms combine together? Is for the sake of stability, and the good thing in chromium is stability is happening by itself because this is half filled, therefore the energy has been decreased. Why it has decreased for manganese further is because even the 4s2 is also filled, therefore it has further decreased in those cases. We see a rise in that because later on, because then there is no half filled and all. If you say for example iron, you have 3D, then you have 4s, so 4s2, 3d6. You don't have a half filled stability or anything, therefore it has increased. Similar minor increases are seen there. Finally, for copper, it has come down to 339 because once again we will talk of the stability, which is nothing but the fully filled stability which is associated with copper. Copper has a configuration of 4s1 and 3d10. Because of this fully filled stability, the enthalpy of atomization is decreased, but why has it decreased so rapidly for zinc coming to 126 is because of the factor that zinc has a configuration of 3d10 4s2. It is not a part of transition elements, we have already seen that. So this configuration will give it maximum stability with complete filling of 3d and 4s, and therefore the enthalpy required for this atomization, which means the enthalpy for stability needed will only be enough, which is equivalent to 126, which happens to be the least of all the elements that are being present. So this is about the enthalpy of atomization factors that are responsible for d block elements. Moving further now from this enthalpy of atomization, let's now talk about the atomic radii. What is atomic radius? That's the first thing that we need to know. Again, a revision of sorts, where if this is the nucleus and suppose we have an atom with say around 3 orbits or so, so radius is nothing but half of the distance in that circle diameter, right? So in the same way, if you consider an atom as a circle, the distance between the nucleus, the central nucleus, and the outermost electron which is present, we can call that as atomic radius. So in this atomic radius, we will now study the comparative studies which are there for 3D series, 4D and 5D, and then we will concentrate our attention mainly on 3D series. So what is this atomic radii that is present? Remember that in any of these second year parts or even for your competitive exams as such, you never need to remember the values which are there, because values will be many. You can't remember all the values, but you need to remember the trends and its reasoning. That is important, be it for public exam or competitive exams. So in the first place, what we have to see here now is, talking about 3D series, this is the green line which is present is for 3D series. This is the atomic radius, and you can see that as you go from one side to another side. First place, what is the variation in atomic radius in general sense? We know very well that across a period, the atomic radius always decreases. This we have studied in S block and P block elements. Why does it decrease? It is because of increase in effective nuclear charge. What is this effective nuclear charge? As we go about, we realize that suppose scandium nucleus has 21 protons. The scandium has 21 electrons, so there is a good amount of attraction between the 21 protons inside the nucleus and 21 electrons which are outside, which are not concentrated at a place. They are concentrated in various orbits like 1s, 2, 3 orbit. In that you have 2s, 2p, 3s, 3p, 3d, like this. So there is a attraction which is present. Now when I go to the next one, it is 22 proton and 22 electrons, which means that the attraction between those two segments are much more now. They are attracting more with a stronger pace. Supposing if I increase this with 23 proton and 23 electron, with an increase in number of proton and electron, we have to realize that the effective nuclear charge, which is nothing but the attraction between nucleus and outermost, will go on increasing. So therefore, when the charge is increased, there is more attraction. When attraction is more, naturally the size will decrease. So the basic understanding is that as we go across, the size should decrease. But what has happened here is at the start it has decreased. That's nice. So it has decreased. After some time we see a certain constancy in that case, and then suddenly it has increased off. I hope you are able to analyze this graph which is present here. It has decreased at the start, maintained a certain constancy, once again increased. Similar is the case with 4D and 5D, where it has decreased at the start, a minimum constancy is maintained, and once again they have increased in the fag end. Now why is this so? This we will study with respect to understanding of 3D series. Let us talk about the atomic radius of M. Now what does M plus 2, M plus 3 indicate is that M is the atomic radius which is present, whereas plus 2 and plus 3 is the ionic radius of the compounds. Will atomic radius be more or ionic radius be more? Once you see these values, you can very well realize that atomic radius are big. The reason is very simple. As an example for scandium, scandium has 21 protons, 21 electrons. When you remove an electron, when you form an ion, it means that one of these is getting reduced and then you are forming it to 20 electrons. So which means that the attraction is now more towards the nucleus and therefore the size will slowly decrease. So earlier the parts were scandium has 21 each, good number of attraction, this is for scandium. If it is plus 1, it will be 21 proton, but outside it will be 20 electrons, so attraction will be more towards nucleus. If it is plus 2, let me write it here. If it is plus 2, it will be 21 proton and this will be 19 electron. So as you go on making these electrons, the attraction will be more and more. So we see in the first place that M has maximum atomic radius, M plus 2 has a little lesser than that, M plus 3 has a little lesser than that. Now why this is so is because as you go on, you can see a decrease 164, 147, 135, 129. A slow decrease has been seen. But then you see some amount of increase in the case of manganese. And then again further there is some sort of constancy maintained and once again there is an increase. This is due to once again giving our basis to stability factors. With more stable systems, we can understand here we also have a concept of shielding effect, where at the start, suppose if this is the nucleus, 1, 2, 3 and the fourth one, this was the fourth 4s electron, this is nucleus and 3d electron. What happened in the case of scandium? You had two 4s electrons, we know the configuration, one 3d electron. There is attraction between the nucleus and electron. Unlike charges attract each other, we know very well. But there is a repulsive case which is present between the 4s and 3d. Because of this repulsion, the size may increase to a small extent. So that is why we see that starting it decreases, but for manganese it is increased because in manganese this is half filled which is stable and the repulsive forces in this become much stronger because there are 5 electrons which are unpaired and 4s2 is also there. So when repulsion is more than attraction, naturally the size will increase. Always remember, attraction brings it closer, repulsion makes it a little far. So because of a stability and more number of electrons, the repulsion is there. But then why this is quite constant in nature? This constancy can be explained with the fact that as the number of electrons increase, say for example 3d6 4s2 for iron, 3d7 4s2 for cobalt, as this increases, attraction between nucleus and electrons is there, no doubt, attraction is there, but repulsion between the 3d and 4s is also increasing. So the force of attraction between nucleus and electron is almost becoming equivalent to the repulsion between 3d and 4s, and that is why there is a constancy which is maintained, but suddenly zinc it rises because zinc once again shows the factor of fully filled stability. Because it is highly stable, the repulsion between these two systems are very high. So the moment the repulsion is high, naturally the atomic radius will increase. Similar is the case with the ionic sizes, where you see that they are almost similar in their cases, depends on their parts. In plus 3 states also, we see that the ionic radius slowly decreases in their cases because plus 3 indicates that the 4s systems generally get out of the parts. For example, when I take it for say iron is 3d6 4s2. When I say iron in plus 2 state, I write it as 3d6 4s0 because 2 electrons are removed from 4s. When I say iron in plus 3 state, I write it as 3d5 4s0, which means that I am getting it more and more towards the stable forms which are being present. So this is the variation that we see for the respect of 3D series which has been present here. Now having seen for this 3D series, we now have to see the difference that is been available for 4D as well as 5D as to why they are so close than the 3D parts which are there. Let's now take up the parts of understanding the nearby presence of 4D and 5D series. There is a difference between 3D and 4D we can see, but 4D, 5D they seem to be very close by. Now that is because we have another series called as lanthanides which will come in between this 4D and 5D series. So these lanthanides which are there, when you fill this 5D series, before filling the 5D series, you will have to fill the 4F parts first. And this segment we call it as lanthanide contraction, which will be studying more in detail when we talk about the inner transition elements. What do we mean by contraction? Contraction means coming together. Because you fill this 4F systems beforehand, there are more electrons and more protons present inside, which will lead to high amount of attraction. This high amount of attraction will lead to something called as lanthanide contraction, which will have similar sizes of these compounds. There is nothing here which is present. Remember that in before 4D you are not filling F block elements. F block elements come only in picture just before 5D, and therefore you can see that these two systems are very close by. So going back to the earlier clearer picture of this segment, we can see that 3D is a little far away, but 4D and 5D series are very close. Their radiuses are very close by. This is because of a factor of lanthanide contraction, which is nothing but filling of the 4F orbitals before 5D, which will lead to more attraction and therefore the contraction of the atom. So for this, let us just see as an example as to what has happened here with the consequence of lanthanide contraction. You can see that the first element has a little far radius, 162, 169, but later on if you see here 144, 145, 134, 134 almost similar, though they are of different series. See, this is of 3D, the 4D and 5D series. They should have had a little bit of difference because more orbits are there. Always remember, 4D is in 4th orbit, 5D is in 5th orbit. So when there is a difference in orbit, you should have had difference. But because of this lanthanide systems, you can see that their radiuses are almost similar or exactly same in some cases. This is what we call as consequence of lanthanide contraction, where lanthanide elements are added beforehand. So this is one aspect of it. We then also see the density of these compounds. What is density? Generally we can represent density as D is equal to mass by volume. Now what is this mass by volume? The mass of these compounds is determined by the nucleus which is present, proton, neutrons and others. Electrons don't contribute for mass. This we have seen in the earlier segments. Whereas volume is dependent on the size of the elements that is present. So if the size of the element is more, it necessarily means that the volume is more because it is occupying more area. But mass will depend on the number of protons and neutrons which is present. So we have a metallic radius size compounds which are there here. So you can see 164, 147, these values we came across earlier. We also discussed why there is a sudden increase here of 137 in this case. There is a sudden increase of 137, and again finally there is an increase because of half filled and fully filled stable systems. Now higher radius means more volume. Mass is already shown here. They have shown these masses, atomic masses. These are the practical mass that are being seen. So what is happening to density here? You can see that at the start the density is almost slowly increasing and there is a good amount of increasing. And that is quite natural because the mass of the system will increase with every single atom. What is atomic number? The number of protons. And when you say this is atomic number 21, it means there are 21 protons. When you increase this, it means there is another proton added, neutrons also will be added. 23 means another added. So naturally with number the mass will go on increasing definitely. So the mass in these parts have been increasing, you can see in this part here. Towards the fag end the masses have come down because of their stability. But what has happened is radius has been similar for this, but zinc radius has increased. Now which means that mass is same but the volume has suddenly increased. And we know by mathematical aspects that if denominator increases, overall value will decrease. So using those mathematical aspects, the density of the compound has decreased for zinc. Except for zinc, for everybody it is following the same trend. For zinc it is decreased, the reason being that the atomic radii is increased but the mass has remained same because of its stability. So these are certain physical factors and general principles that govern the properties of D and F block elements which are present. So having seen these segments for this class, we shall have a small homework where we shall look into some simple questions which are there. Transition elements already well discussed in the second PPT. Mention the general electronic configuration. We have discussed this in the electronic configuration parts. Just think over all this and do it. Any four physical properties. So what are the properties of these transition elements? Remember, transition elements does not include zinc, cadmium and mercury. Define enthalpy of atomization. We have discussed this topic, but deliberately I have not defined this in the segment so that you analyze the topic and form your own definition. Hopefully we can see you in the next class having understood all these segments perfectly, and I hope that this has helped you in understanding various aspects of D and F block elements. See you again. Sai Ram.